Industrial Revolution 4.0. Innovations in artificial intelligence, cognitive neuromorphic, machine vision, robotics, deep learning, and data analytics are enhancing and improving our quality of life. As intelligent machines learn from their environment and execute self-error correction in order to successfully complete a task and ultimately to optimize productivity.
This video deals with kinematical features of intelligent robots, having a sensor located at the arm. A typical sensor might be a force torque transducer or a camera located at the wrist section of the robotic system. With such robot, the motion commands are generated by the sensor, and the robot must execute them in real time. This requires that the robot algorithms include control in sensor-oriented coordinates rather than in world coordinates as in conventional robots. It is claimed that control in sensor or object-oriented coordinates may be comparable in complexity to that required in conventional robots. With a vision sensor attached to the arm, the actual position and orientation of the target are detected. The velocity commands are generated in the sensor in order to move the arm towards the object. Another example is a force sensor attached to the end of the arm and used to assemble a shaft onto the long haul. The required force is constant during this assembly operation. The sensor measures the actual force between the robot and the body and compares it to the required one. The error is translated into velocity command, which causes a motion that eliminates or reduces this error. The Jacobian in the sensor coordinate system. The resolved motion rate control can be used for a sensor coordinate system. In the case of a sensor attached to the arm robotic system, the required velocity of the tool is provided by the sensor. The relationship between the tool velocity given in the sensor coordinate system and the joint speeds. The reference velocity of the tool is obtained by detecting the deviation between the target and the actual positions of the arm with the edge sensor. Angles of the robot by having the position and orientation of the end effector. The inverse kinematics of a serial manipulator is more important than the forward kinematics, as it is essential to move the gripper of the robot to a required position with a defined orientation to grab an object in the position and orientation. There are two approaches to solve the inverse kinematics issue of a robot manipulator. That is mathematical and geometrical. The higher degrees of freedom requires the more complicated algebraic solution. So this segment is devoted to presenting the geometrical solution for the inverse kinematic solutions. The design methodology for the forward and inverse kinematic robotic system. First, moving the hand effector to the robot to a specific location and orientation. Next, calculating the joint angles by the inverse kinematic solution, followed by changing the joint angles to the calculated values. Afterwards, getting the gripper position and orientation by using the forward kinematics solutions. And finally, computing the Euclidean distance between the initial position orientation and the final position orientation to get the error of the two solutions. Inverse kinematics robotic arm using rotational servo motor algorithms and mathematics. Arrangement of the servo motors in this application. The theory allows to position the servos and anchors on the platform on arbitrary places in the plane. Here I use the platform of circular and hexagonal arrangement. The hexagonal platform is the one I have chosen using the hexagonal plates. Instead of having one possible setup, we can imagine 16 where the top plate indicated by the 3 red anchor points can be smaller or larger than the base plate. The motors can be rotated inwards or it can be rotated outwards, and the same for the servo horns. Using a fixed rod of length D between the servo horn anchor H of K and the platform anchor point piece of K. The anchor has a distance of H from the original base anchor and servo shaft. The vector is perpendicular to the servo shaft and is rotated by angle when lifted from the horizontal line. Looking from the top onto the base, each servo can be rotated by the angle in addition to its position base of K. The servo shaft lives in the X, Y plane and is orthogonal to the vector. Using the kinematics equations to find the desired position of the end effector. Forward kinematics uses the joint parameters to compute the configuration of kinematic chain, and inverse kinematics reverses the calculation to determine the joint parameters that achieves the desired configuration. Calculation of the inverse kinematics problem is much more complex than that of forward kinematics, since there is a unique solution. In my project, a geometric approach had been used for solving the inverse kinematics issues. The complexity of the inverse kinematic problem increases with the number of non-zero link parameters and the geometric approach to use to solve the problem. The general idea of the geometric approach is to project the manipulator on the plane and solve the simple trigonometry problems. During the initial autonomous operation, the robotic arm takes the initial start position of the program. Then the arm takes the measuring position according to the study performed for the IR sensor.
As the arm reaches the measuring position, the infrared sensor starts to collect distance measurements between the eye of the sensor and the sorting area. The distance between the sensor and the empty sorting area is set to approximately 14 centimeters. If the measurement is lower than the 14 centimeters, the sensor is set to recognize that an object is placed to the sorting area, and the robotic arm picks it up and puts it into a bucket. The Industrial Robotic Arm Project is a modular system consisting of 6 rotary joints plus the end effector, which is a grip. The rotating joints consist of 1 joint for base rotation, 1 for shoulder rotation, 1 for elbow rotation, 1 for wrist rotation, and 1 for the grip rotation. The 6 servos motors are based on their torque for proper operation. The infrared sensor is a distance sensor composed of an integrated combination of PSD for position sensitive detector, infrared emitting diode, and signal processing circuit. The unit outputs the voltage corresponding to the detection distance. Every rotational joint of the robotic arm is being controlled by servo motors. These motors are connected to the main artificial intelligence microcontroller CPU, which is controlled by the main computer. The sensor is placed in front of the arm above the gripper so that it can read the distance between the gripper and the reflected surface. The servos are powered by the power supply 6 volt DC by the adapter through the main digital section. The distance of the infrared sensor is measured by the position sensitive detector, which translates the measured distance through the IC of the sensor to an output voltage. The greater the output voltage, the greater the distance, the better the distance. The servo motors and the infrared IR sensor. The angle of each servo controlled by the pulse width modulation value, which is defined in this C++ and Python software algorithms. Each of the servos have an IC inside that checks the emitted pulse width modulation of the CPU digital platform and drives the servo to the desired position.